So let's see what you can come up with for questions about polynomial long division. So everybody should think of their best question, and they're going to send it my way. What do you got? What's one thing? What's one question? Yeah, Klaus.
Why do you need to know how to do it?
What's the point? Yes.
I don't understand what leading over.
What does leading over leading mean? What else?
Are there certain cases where this is more prudent than factoring?
Ah, good question. Are there certain prudent? Nice. Certain cases where PLD is more useful than factoring. Any others? Oh, I'm sorry about the spikes in the sound in the video last night. Did you notice that? Towards the end of the video, was there any screeching? Oh, it was the class video. Anybody watch the class video last night? I found that if I talk too loud, that's an interesting reaction. Okay, other questions? Anything else? Anything?
Are there any other methods besides
Other methods than PLD and synthetic and factoring? I'll say that. Okay, I'll answer these then. So what's the point? PLD will allow us to find oblique asymptotes. I'm going to show you that today, but you need to be able to do polynomial long division to actually find oblique asymptotes. What is an oblique asymptote? It's not a vertical asymptote. It's not a horizontal asymptote. It's, what's another word for oblique? Diagonal, slanted. Not vertical, not horizontal. It's any straight line asymptote other than horizontal or vertical. What does leading over leading mean? Well, in an example, let's say we wanted x minus 2 divided into 13x to the 4th plus 2x cubed plus x squared plus x plus 2. There are two leading terms here. What's the leading term of the, what is the x minus 2 called?
What is leading?
I'm going to tell you that, but what is x minus 2? That's the divisor, exactly, divisor. What is the leading term? Leading means first. What's the first term? X. What's the leading term of the, what's that called? Dividend. That's the dividend. What's the leading term? So you do leading over leading, and that's going to be 13x cubed. That would be the first step. Which one always stays the same? What leading stays the same? The divisor leading. That stays static. Which one changes? Yeah, that one changes. As you keep on working down, it changes. Did you have flashbacks to grade school, long division? Did anybody ever? Really? Well, you learned. They never did? So I just taught you long division. Wow, that's really cool. Did anybody ever learn how to take square roots like this? There's a method that was taught up until calculators became widely used, how to find square roots by hand, and it looks a lot like long division. It's pretty neat, actually. Well, no, I mean, if you wanted to estimate to get as accurate as possible, like the square root of 127, do you know how to do that? No. A fifth grader in 1950 could. Just to make it, that could be a show. Are you smarter than a fifth grader from 1950? I like that. Are there cases where PLD is more useful than factoring? What do you think?
Wait, Mr. Seamon?
Yes.
Can we finish that?
Nope, we'll do another one later. I'm not going to finish that one now, but that's just for leading over leading, okay? Are there certain cases where PLD is more useful than factoring? Yes, because not all polynomials are what? Yeah, easily or nicely. It might not be easy, right? But at least it might be nice, nicely factorable. In those cases, what are we going to be doing? It's not necessarily always going to be the case, but we're generally going to be dividing when factoring. When we run out of information to extract with factoring. Are there any other methods other than PLD and synthetic and factoring for analyzing functions? Yep, but we're not covering them. So, let's pause for 1 second here. Okay, let's make one up. Let's say, someone give me a number. I like 3 instead.
What's the point of the question?
Give me another number. 2 sounds great. Another number?
Six.
Yeah.
Okay.
We're going to let that ring, okay? Just ignore it, and that's awesome that it's on. Hi. X minus 1. Was that outside?
Yeah.
How would that be for a superpower? Just be able to think car horn? So anyway, here you go. We just made that up. What are the chances that it's nicely divisible? As in, what are the chances that x minus 1 is an exact factor of 3x squared plus 2x minus 6? Pretty little. It's pretty small. So what we're doing is we want to be able to rewrite this. We want to be able to write that a little differently. So we're going to actually do some polynomial long division. This is a rather nice one because powers aren't so high. What are the two leading terms? 3x squared and x. So you get 3x and you end up with 3x squared. You multiply now, minus what? And now you subtract. This is really important. Please, please put the parentheses around it. I can guarantee you're going to waste about 2 to 3% of the next few days backtracking because you forgot about a negative sign, either in synthetic division or with this. And you'll be sad, you'll get angry at me, but I'm telling you now, be careful of the negative signs. Okay? What do we do now? We subtract. Can someone tell me what's left, real quick? 5x. What do we drop down? Now we have 5x over x is, so plus 5, and we end up with now 5x minus what? So we actually came pretty close, didn't we? What do we end up with? Negative 1. Do we go any further? No, we stop. Can someone tell me why we stop really clearly? Why do we stop at this point? There's no x anymore, but that doesn't, sometimes you, yes, that's true, but there's a different way to say it. What's the power of x right there? What's the power of x right here? You stop. It has to be equal to or greater than to keep going. It is less than the degree of the divisor, so you stop. So, let's label these. What's this called? What's this called? This is definitely one of those questions on the Are You Smarter Than a Fourth Grader? Or what is fourth grader, right? Fifth grader? Who knows? And what's this? Remainder. How would we check this to make sure we did everything correctly?
Divisor times quotient.
Yeah, well, actually, let me write one thing out. We just figured out that 3x squared plus 2x minus 6 over x minus 1 is equal to what? 3x plus 5 plus negative 1 over x minus 1. Because, let's say we did regular long division. 12 into 1, 2, 3, 4. 1, 12, 0, 3, 0, 0. Did I do that right? 0, right? 34. So what's it going to be? 2. 24, 10. So what do we know? We know that 1, 2, 3, 4 divided by 12 is equal to 102 plus 10 over 12. This is the same thing, but with polynomials. The question is, how would we check that? That's what we've rewritten, essentially. That's what we've done. We found a rewritten form of this fraction. How do we check to see if this is correct? We need to multiply 3x plus 5 plus negative 1 over x minus 1 times what? The divisor. You multiply it by x minus 1. Let's do that. Let's multiply that times 3, so you have 3x times x minus 1. You have 5 times x minus 1, and then what do you have at the end? Minus 1, because it cancels with the denominator. You end up with 3x squared minus 3x plus 5x minus 5 minus 1. So you end up with 3x plus 3x squared, sorry, plus 2x minus 6. What is that? That is the dividend. So is it? Did we verify it's correct? Yes. Now here's the point. Here's the point, everybody. We just took this right here. We took that fraction, which was a rational function, and we rewrote it. Do you agree that they're equal? Do you have confidence that they're equal? We are looking at end behavior. What happens as x goes to infinity, and also as x goes to negative infinity? Essentially, what happens to this as x gets huge? Let's look at it in pieces. What happens to 3x as x gets huge? It gets really big. It goes to 3x. It's 3 times the big number. What happens to 5? Nothing. What happens to this as x goes to infinity? It gets really, really, really small. It gets infinitely close to. So what is it getting infinitely? What is the limit? This is a new. Oh, it is 0. What we just found through logic, and this is big kid math language, and you'll use this terminology over and over again next year if you take any form of calculus. The limit as x goes to infinity of 3x squared plus 2x minus 6 over x minus 1, we just found that that limit is equal to what? This goes to 0, leaving you with what? 3x plus 5. Meaning, when x gets really, really big, what does this function look like? 3x plus 5. When x gets huge, the function starts looking like 3x plus 5. When x is smaller, does it go berserk and do some funny stuff? Yeah, but at the extremes, what happens? It looks like a linear function, right? Which linear? Oh, 3x plus 5. So let's actually make one up and actually graph it and see what we can come up with. Let's make up another one. Let's say h of x is equal to. Let's say h of x is equal to. How about x squared plus 2x minus 3 all over x minus 4. If we wanted to do our steps so far, we have dis, var, d. So what should we do first if we're going to figure out the domain? Well, we can actually figure out the domain before doing this. But what's always a good first step that you've been kind of getting in the habit of doing? Yeah, this is equal to what? X minus what? How about x plus 3 times what? Yeah, I like that. Over x minus 4. Didn't really need that for the first one, but it can't hurt. What is the domain equal to? Can someone tell me exactly what the domain is? Raise your hand. Someone who has... Go, Pang. Yes. What about intercepts? Can you, when x is 0, what's y? 3 over 4. Someone said it. There you go. I really should get a buzzer. What are the other two intercepts? 1, 0, and? You need to give me points. So those are the 3 intercepts. Okay. What about symmetry? What do you think? Just look at it. You can tell me. What do you think? It's neither. It's neither. It's neither. Okay. So let's do vertical asymptotes. Can someone tell me what is the one vertical asymptote of this? What is it? Say the whole thing. 4. Yes, that is correct. Are there any removable discontinuities? None. We didn't cancel anything out. Nope. So let's keep moving here. What does the end behavior, what does this look like as x gets really big? What does this look like as x gets really big? Let's check it out. We want to do x minus 4 into what? So up top you're going to get x, and then you get x squared minus, we subtract and we get minus 3 plus what? Then you get 6x minus 24, subtract and you have 21. So what did we figure out? We figured out that x squared plus 2x minus 3 over x minus 4, what does that equal? X plus 6 plus 21 over. So if this right here, let's call that, what did we say this was? Do we give it a name? H of x. So this is h of x right here. So what is the limit as x goes to infinity of h of x? X plus 6. Because what happens to this as x gets huge? What does it get infinitely close to?
0.
It gets small. It gets less and less significant. It gets less and less significant. It's 0. So we have x plus 6. So do you know what that is right there? You just found your first.
So the oblique asymptote is x plus 6.
Yes, y equals x plus 6. Let's put together everything that we've learned so far. We've learned so far that, and guys, we're interested in rough sketches with important labeled points, not super exact. The general idea is what we're looking for. We knew the y-intercept was what? Like 3/4, right? and it has an intercept at, what, 1 and, what was it? 1 and negative 3. There's 1. And we know there's a vertical asymptote, I think, was it 4? What should I put it for? What should I put to symbolize the vertical asymptote? Dotted line, yeah. It's a vertical dotted line like this. Okay, and what about the oblique? The oblique was y equals x plus 6. I'm not going to use the same scale, but I'll use a different color here. So let's say that was 6. Yes, hold on. You do a dotted line. It's not there, is it? It's just a boundary. I need to make more space. Okay. These boundaries keep on going, right? They keep on going. Does this function cross the x-axis anywhere else? No. So let's connect the dots. What is it going to have to look like? It has to do that. Do you have any other options? No. You don't. If this went up, what would it have to cross? It would have to cross the x-axis. If, let's say, could it do this? No, because it would have to cross the x-axis. Can it cross the x-axis anywhere else? No. So it definitely looks like that. What was the domain of this function? Do you remember? It was defined everywhere except for what? So we have, there's something missing, right? We need more. Something on the other side. Now here's the thing. We know it goes down there. So what are our options? It could either go down here or it could do what? It could go down here or what? It could go up. It could go up here. How do we know which it does? Something new for you. Let's look at the degree here. What's the degree of x minus 4? What power? 1. Odd degree equals opposite direction on the asymptote. So if 1 goes down, what does the other side have to do? It has to go up. So just remember this. Odd degree, opposite direction. So what's an even degree? Yeah, same. So we know that goes up. So what's the rest of that graph going to look like, do you think? Use your hand. What's it going to look like? Yeah, it's going to be a little Nike swoosh. Yeah. And what does it get infinitely close to? Yeah, y equals. Think of asymptotes as having really strong gravity. You can avoid them for a little while, but then what happens? It pulls the function in. Let's see what this actually looks like. Let's see if it matches. Oh, look at that, everybody. That is our function. And look at the graph. What did I also graph on there? Yeah, what is that? The oblique asymptote. So did our oblique asymptote, does it match? Yeah. So this is the graph that the calculator pumped out. This right here, is this on the graph itself? No, that's the oblique asymptote. Y equals x plus 6. X plus 6. And the rest, does the rest match? Take a look at this, everybody. Does it match? It's pretty cool, huh? I think that's pretty cool. So we just did oblique asymptotes. Do you have any questions at this point? You might some things might have surfaced in your head. Anything? Yeah, what about horizontal? Also, what about this? When do you have an oblique asymptote? Well, there's 3 cases, everybody. So if we have a rational function and it's p of x over q of x, if the degree, I'm going to make deg of p of x, is equal to 1 plus the degree of q of x, what does that mean? The degree of p of x is 1 greater. Then you have a oblique asymptote. If the degree of the top is 1 greater than the degree of the bottom, you have a oblique asymptote. If the degree of p of x is equal to the is less than or equal to the degree of q of x, what do you think you have? Horizontal. If the degree of the top is less than or equal to the degree of the bottom, you have a horizontal. What's one last case here? So if the degree is 1 greater, it's oblique. If the degree is less than, what's the third case? What? No, we already have equal right there. Greater, more than 1 greater. If the degree of p of x is equal to more than 1 greater the degree of q of x, what do you think happens? Give you a hint. No OA or horizontal asymptote. You actually, in this case, would have a bent asymptote. Are we concerned about those? No, we're not concerned about those. You'd have an asymptote that looks like a parabola. Right now, all of our asymptotes, what are they going to look like? Straight lines. Is that enough for us to deal with?
Yeah.
Given this information, can you have both a horizontal and an oblique asymptote?
No.
No, these are mutually exclusive. Can you have both states at once? No, you can't. They are mutually exclusive. That is correct. So, let's say I gave you this right here. Let's say I gave you n of x is equal to 14x to the fourth plus 2x cubed plus 9 over 13x to the fourth minus pi. Does that have an oblique, horizontal, or neither? Horizontal. Why? They're equal. Yeah, exactly. So now let's talk about, and this is the save. This you'll like this because it's really easy. What happens as x gets really big? What's the only term that really matters in the numerator as x gets huge? Which term is going to get way bigger, way faster? To the fourth, yeah. On the bottom, which one's going to get way bigger? So the limit as x goes to infinity of n of x, what are the only terms that matter? 14x to the fourth over what cancels? What does that value represent? Yeah, y equals 14 over 13 is the horizontal asymptote. If the degrees are equal, is it pretty easy? Yes. What was the other way you could have a horizontal asymptote if the degree on top was less than? So let's say we had 2x squared plus 52 root 5x plus 9 over pi x cubed minus ex squared plus 9. I'm just making it weird. It doesn't matter what they are, right? Does this have an oblique asymptote? It has a horizontal because the degree of the bottom is greater than the top. In this case, what are the only terms that matter as x gets huge? Yeah, the limit, exactly. So it's going to be 2x squared over pi x cubed. Well, what cancels? I end up with 2 over pi x. What happens as x goes really, really big? What's that get close to? 0. If the degree of the bottom is greater than the degree of the top, what is always going to happen? The bottom is always going to get really freaking big, and the top will get big, but will it get the same size of bigness? No. So, what's this horizontal asymptote? Y equals?
2 over pi.
No. 0. As x gets huge, what does, if you plugged in a billion trillion into that, what would that be really close to? 0. If you plugged in a billion trillion, yeah, you get 2x squared on the top, but what would you have on the bottom?
Oh,
Pi x cubed, right? It goes crazy in the middle. Is this thing going to be really weird? Sure. But x cubed, how big does x cubed get? Big. How big does it get compared to x squared? Much bigger. I mean, think about it. A billion squared as opposed to a billion cubed, which one's a little bit bigger? A billion cubed. So basically you can think about it this way. The billion cubed drowns out everything else. This isn't 0, so it's some number over a billion googolplex mazillion. What does that get really, really close to? 0. So in this case, the horizontal asymptote is 0. Exactly. Very good.
So
if it's less on the top.
It's going to pretty much always.
Oh, it's always 0. So what we can say about that, therefore, everybody, if the degree of p of x is less than, strictly less than, the degree of q of x, then HA is what? Y. You have to say y equals 0. Does that make sense, everybody? Or it's okay if it doesn't make complete sense right now. That's fine. So there's one last little bit of factual information I need to impart to you. Vertical asymptotes. Can you cross them? You can't cross them. You know that. Because they either spike up or down or both down. What about horizontal asymptotes? Oblique asymptotes. Could you cross one and it still be a function? Yeah. So what do you have to check? If you find an oblique asymptote and you find a horizontal asymptote, what do you have to check? If they cross. So how would you do that? Let's look at this original function here. We worked on, what was that one we analyzed? This one right here. We saw this one, right? There's our h of x. And what was our oblique asymptote on this? Do you remember? It was x plus 6, right? So we have this function right here, and we want to know if it crosses x plus 6. How do you find out if two functions intersect each other? Yeah, you set them equal to each other and solve. If they intersect, they have a common solution. The graph of a function is the set of all solution sets. So where two graphs intersect is where the common solution is. How do you solve this? There's no trick involved. What do I do? Yeah. Yeah, so you have x squared plus 2x minus 3 is equal to x plus 6 times. Yeah, and what do you have to do now? Well, you leave this the same. What do you do to the right-hand side? Yeah, you have to distribute. You get x squared plus 2x minus, what cancels? And the 2x, what are you left with? What does that mean? Assuming you did all the math correctly, it means they do not intersect. So the last acronym, and we came up with this last class. I've been trying to come up with the best acronym for all these different things. We have horizontal asymptotes, we have oblique asymptotes, and you also have to know where they cross, if they cross. So we had three things. The best arrangement we could come up with was Hakoa. That's the best one we could come up with. You can't separate the H and A. You can't separate the O and the A. So what does that mean our acronym is? I've tried coming up with better ones. The problem is if you try to make it better, you have to choose different words, and then it's harder to remember what they stand for. So we have Disvard Hakoa. It looks almost like cocoa. Like I really want it to be cocoa. It's just not, though. Can't get that H in there. Hakoa. Hakoa. Hot cocoa. So, okay. So, your homework tonight, and we still have a bunch of class left, so please don't pack up yet. You're going to, there's the first part of what I want you to do. I want you to graph R1, R2, and R5 by hand. I want you to watch Rational Functions Part 5 and come up with at least 2 questions. And it seemed like the class really didn't want the test to be on Friday.
Yeah, please, Monday.
Monday?
Yeah.
You guys in favor of Monday? So we'll have it on Monday. And the other thing I want to add in here, I want to add in this. Can you come up with a better acronym? And you can use different letters as long as it makes sense. Something that can be something that you can memorize. Okay? We'll have a little contest. There are some great online generators for acronyms, everybody. Yes. Okay. Okay. Thank you. Okay, and with that, I would like you to start working on your homework.